Chord. Get it? I'll begin. I'll begin again. Dear Father, we thank you for this day. Thank you for your students. Pray you to help us use this time wisely, just to learn a little bit more about your creation. Lord, in your name I pray. Amen. Well, guys, I will say this, by the way. So grading your test, it's wild. Like you guys get like what I would think of as being elementary problems. They're just off the wall wrong answers on some of them. But then the harder problem, like half of you got spot on. We really find it very disturbing. But anyway, we'll look more at that tomorrow. So I want to talk to you about differential equations. And so this is the start of a discussion that ultimately leads to Math 334 here. But that demarcation in material is kind of artificial and just a part of our education system. Truth be told, there's a lot of differential equations that you could solve already with the kind of math that you already know. So the kind we'll talk about in here are ones that look like this. dy dx equals to some function of x and y. So this is a differential equation, first order. Oh, okay. I thought you were making some kind of like animal noise or something. It's a very, very strange sounding water bottle. Okay, you can't recreate, no. So if it's just the differential equation, to solve it, right? What does it mean to solve a differential equation? Well, sometimes we have more information than this. Sometimes it's paired with a condition, say like y of x naught equals to y naught. So this is an initial condition. And so if you take the differential equation paired with the initial condition, it's called an initial value problem. All right? Here, let's start small. What if we have dy dx equals to 7 and y of 0, well, let's say y of 1 is equal to 2. Can you solve this initial value problem? What can we do to undo differentiation? Right, we just integrate. So if we integrate dy dx, well, that's equal to the integral of 7 dx, right? But what's this? This works out to what? Well, the integral of dy dx is just what? Y, right? And this is what? 7x. And then we have to add a constant, right? All right. And then what? Well, that would be this right here. If I was to box this would be what's called the general solution. All right. To star, I'll give it a name. All right. Now, how do we solve the initial value problem? We just have to fit the data, right? Plug in 1. So y of 1 is equal to 7 times 1 plus c. And that's supposed to be equal to what? It's supposed to be equal to 2. That's given, right? Just to be clear, I know sometimes you guys get lost about what we're doing versus what we're given versus what we're finding. Everything in the red box is what's given. Everything below it is what we're finding, all right? So what does that mean? That says c is equal to what? Yeah, c is equal to minus 5. And therefore, y is equal to 7x minus 5. There you go. That's the solution to the initial value problem. So sometimes we can solve a differential equation just by plain old integration, right? In fact, I teach this in Calculus 1. When I do Calculus 1, I'll teach this before I even do like the area problem. We talk about anti-differentiation as a means to solve initial value problems. Here's another example. Example 2, what if you had dv dt equals to minus g with v at time 0 equal to v sub naught? It's actually fairly apparent that you don't, do you really need to do this? Do you really need to write this down like this? Or is it already, there's a theorem. There's a theorem in, how to say this? What is a solution to a differential equation, really, is my question. Let me just write down the answer here. So v of t is equal to minus gt plus some constant. All right. Now, I would argue that this is simple enough that you can just see that. I know this is true. It's correct since d dt of minus gt plus c is equal to what? Minus g, right? So, plugging, v equals to minus gt plus c into star works. And that's what it means to have a solution to a differential equation. If we plug it into the differential equation, the equation's true. You've had homework problems about this for more complicated differential equations earlier this semester, you remember? Like really early on, we asked you to show certain functions or solutions to like partial differential equations, uxx plus uyy, or something like that. That was way, way back. It seems like forever ago, right? The first couple weeks of the class. Now, that'd be a general solution, right? But if we plug in times 0, what do we get? Minus g times 0 plus c, that's supposed to equal to v sub naught. So this gives me that c is v sub naught. Therefore, the solution to the initial value problem here is v is equal to, I'll write the v naught first, v naught minus gt. Now, perhaps you've seen this before, right? That familiar? Should be familiar. This is the constant velocity formula from Physics 231, right? Constant acceleration, I should say, minus g. Now, this method falls flat if we try to do something like this. What if we wanted to find velocity as a function of position in this context? Find velocity as a function of position with where acceleration, which is dv dt, is equal to minus g. So the long, complicated way to do this would be to integrate again to find the position as a function of time and go through the whole deal. But here's a kind of sneaky, better way to do it. You can take dv dt and rewrite that as dx dt times dv dx in one dimension. This is by the chain rule. So in other words, I'm trading v as a function of time for v as a function of x. And so what is this? This is, but you see what you got here. This is dx dt times dv dx. In other words, that's v dv dx. Gives me joy to say. So v dv dx, that's my acceleration, right? But in this context, I'm thinking about constant acceleration of minus g, right? So let me just summarize. Where a chain rule and physical motivation prompts me to try to solve this differential equation. So the differential equation I'm looking at here is this. Can we solve that? I can't just integrate this time, right? Because the trouble with just integrating is I've got that v. I don't just have, like over here we had dy, dy dx. We integrate with respect to x. We undo the differentiation, right? But now we've got v dv dx. I can't just integrate with respect to v, and there's an x there. I can't ignore it. So this is where separation of variables comes into play. Separation of variables, it says you just treat the differentials as if they're little small quantities and do algebra on them, and then you integrate. So in particular, this gives us v dv is equal to minus g dx. Right. So we use this differential notation, and then once you've separated variables, g is a constant, you can integrate both sides. And I'm going to do this the smartest way I know, which is to integrate from, say, v1, from v, say, v naught to vf, and I'll integrate the other side from x naught to xf. The mathematical justification for what I'm doing is just this u substitution. You have to match the bounds, right? This is really just a slick notation for a u substitution theorem. But anyway, what happens here? This side gives us 1/2 v squared, evaluated from v naught to vf, and the other side we've got minus gx, evaluated from x naught to xf, right? So you do the fundamental theorem of calculus, you got your 1/2 vf squared minus v naught squared is equal to minus g times xf minus x naught. And then what? We'll solve for vf, usually what we do. So vf squared equals to v naught squared minus 2g xf minus x naught. You might recognize that formula. This is the what? Sometimes we write that as a delta x in 231, you know? Maybe you recognize it that way or with a delta y. That's the timeless equation, as we usually call it, right? So the technique I just used to derive that is what's called separation of variables. Okay? Now you notice I've built initial conditions in with a kind of sneaky move. I integrated over matching bounds that built the initial condition in. That's another way you can do things. Yeah?
On the right side of the equation, should an initial value be also squared?
Oh, yes, thank you. You are correct. Here, let's look at a much more mathematical and completely uninteresting from a physical perspective example. Okay, so what if we wanted to solve dy dx equals to x squared y? How would you do that? We cannot just integrate because the trouble is the thing we're trying to find is y, right? So in order to actually integrate both sides, I need to know the answer at the start. So that's why I can't do it like example 1. I can't just integrate. It's not possible. What's that? Well, I know, like example 1. See, example 1, I had a derivative with respect to x set equal to something I know how to integrate. If I have a derivative equal to something I know how to integrate, I can just integrate both sides, and that gives me the solution.
So why can't you divide by y multiplied by dx?
Oh, yeah, that's what we're going to do. Yeah. You're way ahead of me. So wait a minute. Why, you could have left class early. You already know this. That's good. I mean, it's good. This is a problem we like to have. Does that mean you get an A? In what? In class. You can have an A for class today, yes. But unfortunately, it's not in gradebook, and it's not worth actually any course points. So it's kind of like the whoa. See, I was about to say something that I would have had to edit the video later. What are you trying to do to me? It takes time to edit these videos. Let's see here. So yeah, we separate variables, and then we integrate both sides. Okay? And so that gives us the natural log, the absolute value of y, is equal to 1/3 x cubed plus a constant. Now, you might wonder, well, here, let me just, since we're starting, let me add a different constant to both sides. So c1 on this side, x cubed, plus c2 on the other side. Why did I don't do this. We're doing two different integrations. It seemed like there might be two different constants. But pragmatically speaking, you really can just package them into one single constant. Because that's just as general an answer. That c is, if you like, it's c2 minus c1. That's just as general an answer as having two constants there. The goal in solving this problem is to find as general a solution as possible. Now, this, I could put a box around this. This would be what we call an implicit solution. So implicit solution, implicit means basically not solved for y. Y equals function of x, you know? So that's an implicit solution. These are okay, but we really like to find explicit solutions when we can. In other words, solve for y. Can we solve for y here? Let's see here. What would our first? My first move would be to take the exponential of both sides. So the exponential of the natural log of the absolute value of y is equal to the exponential of 1/3 x cubed plus a constant. Now, exponential of the natural log gives me back, these are inverse functions. So that just gives me absolute value of y is equal to, well, e to the c times e to the 1/3 x cubed by laws of exponents. I just did. Yes. I mean, that's not like sometimes I'll say things like, I think the speed limit signs are wrong, because obviously everyone's going faster than that, I have not actually ever tried this kind of humor on cops. I think it might go badly. But, I mean, like most laws, they're really a license for extortion by the government, right? But, sorry. We're not supposed to say these things. Oh, see, what's up, Matt? Square on both sides. Well, this is absolute value of y. So what I can say is this. I can say that y is equal to plus or minus e to the c times e to the 1/3 x cubed, right? And that's such a hideous formula. We might as well just take this plus or minus e to the c and just call it k, right? So our solution actually has the form y equals to k e to the 1/3 x cubed. And short of having initial, if we had an initial value given, we could figure out what k should be, right? Now, following my derivation, there's one value that k cannot be logically. 0, right, because it's plus or minus e to the c. Very good. But my question to you is that an artifact of our calculation? Is y equals 0 a solution? Look up here. If we put y equals to 0, the function, the constant function 0, the 0 function, is the derivative of the 0 function 0? Yeah, it is. It is constant. Get true to your. I'm going to miss you guys. Let's see here. So that's 0. And of course, x squared times 0 is 0. So yeah, 0 works. Why did we lose that? Well, there's a very simple reason. We divided by y. So in this step, going from here to here, we lost y equals 0 as a potential solution because of that step, that algebra step. So y equals 0 is what's called an extraneous solution to the method. I sometimes tell students that if I was to be a rapper, I would be called extraneous G, and my tagline would be that I'm not even in the solution set. But, except I would say more like, I'm not even in the solution set. See, I've thought about this. What's that? What, no? I don't have the life experience? What, no. Let's see here. So,
you got a sample for us?
I do not. I have no mixtape. No. No, I do not. Anyway, so this is the explicit solution. All right. In fact, it's also the general solution because it by a quirk of fate we've included y equals 0 as a special case. Like we pick up when we put k equal to 0, we recover what we lost. But that's just kind of an accident of the algebra here, right? So there you go. That's explicit solution. So later you can tell your RA that you saw explicit material in math today. But, sorry. That is not my joke. I was at a professional math conference once, and the speaker put a warning up. He said, "Warning: explicit material ahead." We're like, and then the next slide had just an amazing mess of equations. So I was amused. Anyway. All right, I'll shut up. See you guys tomorrow.